Welcome to my graduate student video presentation. My name is Wesley Chavez, and I'm going to be talking today about this paper published in 2001 to proceedings of the 34th International Symposium on Microarchitecture. The paper is called Reducing Set Associative Cache Energy via Wave Prediction and Selective Direct Mapping by Powell, Agarwal, Vijay Kumar, Falsafi, and Roy from Purdue and Carnegie Mellon. Alright, so let's talk a little bit about what a cache even is. It is a way for the processor to get memory faster than going all the way to disk memory. So we have a processor and usually an L1 cache on the same die, on the same chip. A little farther away we may have an L2 cache and an L3 cache before the disk memory. And the processor checks the caches to see if the memory that we need is in the cache before going all the way to the disk memory. L1 cache is a lot closer, and it is smaller, and it is way faster to access than going all the way to disk memory. So we'll want to find most of our memory in the caches before we go all the way to disk. So L1 cache is a lot smaller, a lot faster to access, a lot more expensive, and all the way over on this side, disk memory is very cheap, very slow to access, and a lot bigger than the cache sizes. So in this paper they talk about four-way set associative cache. What that means is for any address of data that we're trying to look up, the data in L1 cache, or any of the other caches if they're also set associative, the data can be in any one of four ways in the cache. So the way we figure out where the data is sitting in the cache is we compare a tag. A tag holds part of the address that we're trying to access, and the correct tag, this is a simplification. The middle two hexadecimal numbers correspond to the tag. So if we're trying to look up address FFFF in memory, we compare the tag. Oh, here's FFF, or here's FF, which is the space designated in the address for the tag. Yes, FF. So this would be the memory slot, or the way that we're trying to access. So the thing that caches do in order to access the correct way, they do a couple things. One is checking the tag and checking all the data ways in parallel at the same time in order to find the data. So it would check all four tags and all four data spaces, data ways at the same time, and once we get out the data, we already have the correct tag, and we just choose the data way that corresponds to the tag. Another way to do it, to save energy, would be to check the tag first, then only probe the corresponding way if we have a tag match. So that saves energy because we don't have to probe the other ways that the data may be sitting in. And this paper is all about energy savings. How can we save energy in the cache? So I went over the two ways we can access the data in the cache. We can do it sequentially, which is check the tag, then check the data. That's a little bit slow because we have to check the tag, and only after we determine a hit, checking the data. It's a little bit slower. However, it is energy non-intensive. The other way, in parallel, checking the tag while checking all the ways of the data, is a little bit more energy intensive because we have to probe all the different data ways. But it's faster because we already have the memory at the time that we determine a tag hit or miss. Now, what if we can choose the correct way? What if we can predict the correct way while keeping it parallel. And that's the idea of the paper, is that while checking the tag, they only predict one way that the data is sitting in. And once the tag has been determined a hit, we already have that one data, and we've saved 75% energy because we didn't probe the other three ways. If it's a miss, however, we'll have to go back and predict the second way while predicting the second tag. Hopefully it's sitting in there. If not, we got to keep doing this over and over again until we find the correct way that the data is sitting in. Way prediction and selective direct mapping are two different ways of giving a prediction for the way that the data might be in. Way prediction uses either the load PC or what they call an XOR approximation, an approximate data address formed by XORing the load source register with the load offset. Now, I'm not entirely sure what this means, but it gives a clue as to which way the data might be in. With selective direct mapping, we count how many times data is evicted from one of these ways, and the more likely it is to be evicted, the more likely we are to not find it in the cache, so we can eliminate that one way or the three ways that are victimized most or sent out of the cache because we don't have enough space. So way predictions more suitable for instruction caches, and selective direct mapping is more suitable for data caches. Let's quickly go through a few figures they have included in this paper, and let's check out how they did. This table says the relative energy of operations relative to a parallel access cache read that's probing the tag and the data at the same time in a four-way set associative cache. Sequential access way predicted or direct mapping access is 21% of that in terms of energy. Cache writes, 24% of that. Tag array energy, 6% of that. That's just probing the tag. And this 1024 entry by 4-bit prediction table read write, that's denoting the lookup tables that the selective direct map and way prediction uses, because they use this table to actually generate the prediction, and it's very, very cheap to do, energy-wise. All right, so a little note about the tables, about the graphs in this paper. They are kind of ugly because they double up on graphs. So in this one, E, PC-based, X, XOR-based, E and X right here. And they doubled up on the graph by showing the relative energy delay for these, lower is better, and performance degradation, lower is better, for PC-based and XOR-based way prediction. So we see a little bit less energy in the XOR-based approximation for way prediction, but not too much performance degradation, so that's kind of nice. Here is some way prediction accuracies these are for different data sets they tested on. Different way prediction accuracies, they get somewhere around 60 to 70% accuracy of the 60 to 70% accuracy. In the end, they give a figure of 77% accuracy for way prediction of data caches. So that's the final answer they use. Maybe that's an average of all of these or something. So I guess we'll see. All right, here's a little table for miss rates in the data caches in direct map versus four-way set associative caches. We get less miss rates in the four-way set associative caches for most of the data sets. All right, some more doubled up graphs, which I hate. Okay, A is 16K, B is 32K, so they compared different cache sizes and how much energy delay or energy savings and performance degradation they get with their setup, with the way predicted and selective direct map setup. So as you can see, a little less energy on the 16K caches versus the 32K uh, size caches, but not much performance degradation difference of in either of the cache sizes. This one on the bottom, it's an access breakdown, 0 to 100%, direct mapped, way predicted, and misprediction. So they did selective direct mapping. So sometimes the ways are direct mapped based on um, their direct map based on their predictions. They may only have one way that we can probe. Way predicted and misprediction. Um, so we want less mispredictions and more way predicted, more black. So that's a kind of idea of their accuracy. Right. They compared two-way set associative, four-way set associative, and eight-way set associative caches for the same relative energy delay. Remember, lower is better. And performance degradation, again, lower is better. We get a lot less energy delay in the eight-way set associative cache. Makes sense. And for this swim data set, I don't know why they have so much performance degradation. And I believe I'll have to go back and check why they get so much performance degradation. I'm not sure I remember if it's in here, if they included the reason for that. Let's go on to the next figure. This is for selective direct map plus way prediction, selective direct map plus sequential, and sequential. So we get less energy in the second one, which is selective direct map plus sequential. And we see a high performance degradation for just the sequential accesses. That is because um, of the cache access times. It's a lot slower with sequential because we're comparing the tag, then going to the correct way to find our data instead of doing all that at once, realizing we had a tag match, and then using that data. So that's pretty interesting. I'm going to skip over this graph for now. This is a very important one. This is energy savings and performance degradation. The line in the middle is energy delay savings for perfect way prediction. So if we predicted the correct way where the data is every single time, we're gonna be sitting at this line. However, more realistically, they don't predict the correct way every single time, so the energy delay is a little bit higher. These are for all the data sets. Yeah, so let's see how they did in the end. For way prediction with instruction caches and kind of a combination of way prediction and selective direct mapping in data caches, they see data cache energy delay reduction of 69% and an instruction cache energy delay reduction of 64%. That's quite a bit. That's pretty awesome. The performance degradation of these techniques is less than 3% compared to, I'm not sure what they mean by aggressive, but compared to a four-way set associative parallel access cache that's probing the tag at the same time as probing the data. Less than 3% performance degradation. That's because sometimes they did not predict the correct way, so they'll have to go back and choose a different way. Hopefully the data is sitting there in the second way, but if not, they're in trouble. So it takes a little bit longer sometimes than checking all the tags and checking all the data. In the end, they get 77% corrective way correct way prediction in the Dcache, which is pretty interesting. And I think that's all the figures I want to go over in this paper. Um, Thank you for listening, and I hope you learned something today.